Okay, so I want to just carry on with these notes. I'm going to finish these notes so that tomorrow you can have some time to practice the questions. Okay, this might get a bit ugly. I hear a storm coming. Okay, so what we are looking at, this is a continuation of those last three. Remember, there are, I think, six of them, and so we've done three before. Okay, so here is the next question you ask. Are they non-polar and polar molecules together? So in the last one I asked you, are there polar molecules? Are they non-polar molecules? And then we looked at those. Now we're saying in the same container, the same beaker, for example, we have got a whole bunch of polar molecules, and inside there we have non-polar molecules. So for example, if oxygen is dissolved in water. Now this happens often, because if you think about fish breathe the oxygen from water because it's dissolved in there. So the gills take the oxygen out of the water and it's dissolved in the water. Okay, so what's happening now, I have got a bit of a diagram there for you that I found, but what is happening, sorry, I should have done my dots. Okay, so what you can see is if we make our water molecule, so this is my oxygen with my lone pairs, this side is negative and this side is positive. Okay, it's a neutral molecule, but it has poles. So this would then be considered as my dipole. Okay, it's a polar molecule and that's a dipole. Now, when we have oxygen, okay, and oxygen is a diatomic molecule, and it's pulling equally on either side. Okay, but remember, this one has a negative side. So remember, these are sharing electrons. Sorry, my gate is knocking. These are sharing electrons. Okay, so what is happening is that because it's so close to this water molecule and the negative side of this water molecule, those electrons start moving to that side. Okay, so here's a nice diagram. It shows that the electron cloud is pretty evenly spread, and this is because this is nonpolar. And here we can see this is slightly negative, slightly positive. And with the water coming close here, it pushes the electrons. So we have a bigger electron cloud on this side, making this side negative and that side positive. So even though this is a non-polar molecule, we have induced, remember the temporary, we have induced a dipole. Okay, so we have induced a dipole, causing electrons to move to that side and making this side negative and that side positive, because that negative is repelling those electrons. And so this is called a dipole induced dipole force, and it's between a polar molecule and a non-polar molecule within a container. Okay, and it's the dipole is forcing the non-polar molecule to become a polar temporarily, and there's this force of attraction that happens between there, and that force is then called the dipole induced dipole force. Okay, hope that makes sense. I do want to point out though that London forces are pretty much present everywhere, because even if this wasn't happening, remember these electrons do move around, and so all of the interactions between particles can have London forces as well as the other ones. So at the very, very least, you always have London forces. Okay, now here's the next one. This is important because this is now we're saying, are there ions involved? Okay, I'm going to go to this side first. Are there ions involved? Okay, so if we have a non-polar molecule substance and we happen to have ions in that substance. Okay, so this is where we have cations and anions with a non-polar molecule. So here we have iron, and it's a positive anion, and here we have a non-polar oxygen molecule. So it pulls that side, it's fine. Now, because this is positively charged, there is some sort of attraction and repulsion happening here. Well, attraction, okay? The electrons that were over here, the electrons that were over here are now being attracted to that side of the molecule, because this side of the molecule is close to that positively charged particle. And remember, opposites attract. So the electrons which are negative are attracted to that ion which is positive. And so the electron cloud, if we had to draw the electron cloud, would be bigger on that side, because it is attracting, the electrons are attracting, they are being attracted by the positive ion. Okay, and there you can see, I don't know what they've done here. This is not my drawing, just don't worry about that. Okay, so that's what's happening over there. If this was a negative ion, then the electrons would be forced away and we would also induce. So this is an, excuse me, this is an ion and this is another induced dipole. So I think you can see here, whenever non-polar molecules are involved, you're pretty much making temporary dipoles all the time. You're making temporary polar molecules. So it's just, what else is it with? So an ion will cause a non-polar molecule to be a temporary dipole. So this is called an ion induced dipole force. Okay, when there are ions involved. How do you know there are ions involved? Because a substance that is ionically bonded will then break apart or dissolve. Okay, please remember that all the intermolecular forces that we've been dealing with up until now are only between molecules, so covalently bonded molecules. Anything that's ionically bonded is separate. They don't have intermolecular forces, they just have the electrostatic forces that cause them to hold together. But now they've split up and they are now influencing everything else. If you have ions with a polar molecule, now remember I said water is a polar molecule, but the attraction between water molecules is hydrogen bond forces. But take a look here. This is, for example, a salt solution. So here it's NaCl. Okay, so the green is Cl, the blue is Na. Now take note of what's happening here. Look at these negatives. Can you see that the positive side of each water molecule is surrounding the negative ion? And look at this positive ion. All the negative sides of the water molecules are being attracted to those positive ions. So the positive sides are attracted to the negative ion and the negative sides are attracted to the positive ion. And that is how salt will dissolve. Anything that's ionically bonded that the water can pull apart and break their bonds will then dissolve like this. Okay, where you've got this force of attraction now between this positive ion and negative side, and this negative ion and this positive side, and this is now called ion dipole force. Okay, you can put force after each one of these, it's no problem. Okay, ion dipole. Why? Because look what's there. There's ions and there's polar molecules, so it's a dipole. Ion dipole. This is a non-polar, but it's induced into a dipole. There's an ion, so it's ion induced dipole. Here we have a polar and a non-polar molecule. We have a dipole and we have an induced dipole. It wasn't a dipole, but we made it into a dipole. I really hope you're understanding this. Okay, so this is a summary of everything we've done, so don't freak out when you look at this now. It's just a summary. Now, one thing I want to point out, please take note that these are called van der Waal forces as well. Now, sometimes you can call these three under here, dipole, dipole, induced dipole, and London dispersion forces. You can call them van der Waal forces. If I ask you for a specific intermolecular force, then you'll have to give me those. But a van der Waal force is generally okay. You'll notice that there's numbers and they don't go up in order. It goes 1 on this side, 1, 2, 3, 4, 5, 6. Now if you look here, it says here, the numbers under each IMF list list them in order from strength. So the intermolecular forces, again, they are between covalent molecules. We don't talk about anything ionic here, so don't fall into a trap. Okay, this is covalent molecules. Okay, covalent molecules. Okay, please, please, please. Anything ionic has ionic bonds. That's it. There's no forces. Remember, these are individual, and I'll explain just now when I do the giant structures. Okay, so one being the strongest. Hydrogen bond forces. I want you to remember to write forces because that will help you. Hydrogen bond forces is a 1. They're the strongest. Then we have iron dipole. Then we have dipole-dipole. Then iron-induced dipole. Then dipole-induced dipole. And then London dispersion forces. So London are the weakest. So generally things that only have London forces are gases or have very low boiling points because they can break up quite easily. Okay, but everything else is there. All right, so I want to just talk about hydrogen bonds. So you see the arrow going down here. So the strength of a hydrogen bond force is dependent on how many hydrogen bonds can occur. This means how many sites of hydrogen bonds are there. So example, water has more sites than hydrogen fluoride. So water will have a stronger intermolecular force than hydrogen fluoride. Now, I'm sorry, this didn't become very clear, but what this is that it's hydrogen with fluorine, okay? And the fluorine has a hydrogen, let me use another color, has a attraction between another fluorine. Okay, there's the attraction, that little red. Whereas water, oxygen, H, okay, I'm making it a bit bigger here than what it is. It can then have a, there's an H and an O and an H. All of a sudden I'm just working sideways now. An H and an O. So here what we have is, where's my red? Okay, so here's an attraction here, and here's an attraction here. For every water molecule, there are 2 sites where a hydrogen bond can occur. Whereas here, there's only one side. There's hydrogen with its F, and there's another molecule over there, and there's the attraction between those molecules. So the more oxygen, or the more hydrogens oxygen bonds with, the more sites there are. This is good to know for organic chemistry, girls. We are going to do this in organic as well. So technically, ammonia will have the highest or the strongest intermolecular force, the strongest hydrogen bond forces, because ammonia is bonded to 3 hydrogens, and so you have 3 sites for other molecules to be attracted to it, okay, and cause that strong force. But remember, there are still there are still London forces, yeah. Okay, here we have, because London forces are created by movement, so we're talking about London forces here. They're pretty important, both of these forces, because London forces are created by the movement of electrons to create dipoles, and hence electrostatic forces. Electrostatic forces just mean you've got an attraction between a positive and a negative, okay, but they're called electrostatic forces. All interactions between particles will have some sort of London forces. So that's what I've been saying. Anything, so even water can have London dispersion forces and hydrogen bonds. Okay, so be careful with that. In other words, all of these now also have London dispersion forces. But if you've only got London dispersion forces, you can't have all of those. Okay, so factors that influence the strength of the London forces or the London dispersion forces are the number of electrons. Now think about it. It was the movement of electrons. Remember, the electron cloud moves and gets bigger on the one side or smaller on the other. So the more electrons you have, the bigger the force of attraction. So here we have a big atom, and a big atom, there's a lot of electrons here. And here we have a small atom and a small atom with fewer electrons. And so we have a strong force of attraction between these atoms, but a weak form of attraction between those atoms. Please remember, these are not bonded, they are just atoms. Okay, but I'm showing you that the bigger the molecule, the more electrons there are, the stronger the London forces will be between the molecules. The more electrons, the stronger the force. Then the second thing is the interacting surface area. This is mostly in organic chemistry, but I want to just bring it up here as well. So here we have a single atom and a single atom. There they have a force of attraction, or let's just call it a particle, not an atom. Let's just say there's a particle and a particle. Could be a molecule, because this side's negative, this side's positive, and we have a weakish force here. Now look what's happened here. Here we have a string of these particles and a string of those particles. So there's 1, 2, 3, 4 forces that is happening between here. So this creates a much stronger London force than just between the two. Okay, so think of it as, imagine a bunch of threads of cotton, and you put one thread of cotton between something. It's quite weak, you can break it. Now you put a whole bunch of cotton together and you try and pull that. That's a lot stronger, okay, and you're going to need a lot more energy to break that. So that's where that is there. Okay, page 3. This is going to be a long video, I'm sorry. Okay, page 3, physical properties and IMF. So we've looked at the intermolecular forces. We're done with the intermolecular forces. We're now going to look at, well, what does it influence? How does it, what does it do now? And we are specifically going to look at melting points and boiling points. Now, girls, there are other things in your textbook that you will see that it's influences. We don't do that. I think they've taken it from a government book. You can even see the SAGS document. We are only looking at melting points and boiling points. Okay, so melting points and boiling points are the temperatures where a substance changes phase. Okay, relatively, it's solid to liquid for melting points, and liquid, or not, sorry, respectively, solid to liquid and liquid to gas for boiling points. These temperatures are influenced by a number of factors, okay, but most especially intermolecular forces. It includes pressure as well. Okay, so we're just going to look at solids. So here we have giant covalent structures. These share electrons. Okay, these are not ions. There are 3 specific ones you need to know. Silicon dioxide, there it is there. We've got some silicon with your oxygens, and they make a giant structure. So in other words, it's not just this single little molecule that is there, and you've got all these single molecules. They actually fit onto each other, and you land up with this structure that carries on and becomes this giant structure. Okay, sometimes they are called macromolecules. A diamond is very similar to this. Remember, they are just made of carbon atoms. So carbon is then bonded to another carbon, which is bonded to another carbon, and another carbon, and so it carries on. Again, covalently bonded, not ions. Then we get graphite. Graphite is also just carbons, but you can see there's a different thing happening here. We have weaker forces between the carbons here and here, so they like plates. And then these are bonded covalently, so the top plates are bonded covalently like that, and then beneath them is another plate, and they're not bonded covalently, they just forces. And so that's why you have your pencils. So if you think of a pencil like this, now I've got my pencil, and we can write, because these plates of graphite just come off, they break off, it's so weak. It's funny that that does that, and it's made of carbon, but diamonds are the strongest substance known to man, and it's so strong, and it's made up of the same stuff. Okay, now we're looking at, let's just read here. The atoms in these macromolecules are held together by strong covalent bonds, and so they require a lot of energy to break. So if you want to melt a diamond, you are going to need a hell of a lot of energy. And just think about what makes a diamond is the lava under the earth. And so you're going to need a huge amount of energy to melt a diamond. Okay, so they have very high melting points and boiling points because they don't have a force to overcome. They have actually got bonds to break. Okay, that was a very important sentence I just said. They don't have a force to overcome. They have bonds to break. Okay, giant ionic solids. So these are all our ionic stuff. Okay, remember, we don't always get these massive big chunks of crystals. We break them up into powder, but it's still ionic, and they don't have intermolecular forces. Okay, this is ionic lattice structure. The melting points and boiling points in ionic solids are determined by the electrostatic forces. So remember, we've got a positive sodium here and a negative chlorine. Here I've got a fluorine that's negative and a positive sodium. Here I've got a negative oxygen and a positive magnesium. These are all ionically bonded substances, and it depends on how strong they are attracted to each other, depends on, well then, the boiling points and melting points would depend on that. So all ionically bonded particles do not have IMFs or intermolecular forces, but are held together by ionic bonds. But they still have very high melting points. So remember, it's like melting salt, for example. You can do it, but it takes a lot of energy. Okay. Now, this is what we've been dealing with this whole time, are simple molecular substances like water, like all the other molecules we've been dealing with intermolecular forces. They are independent, standalone molecules. These are structures. They can cause crystal lattices. But these are my independent molecules. So HCl, water, carbon dioxide, the molecules in organic chemistry, all of them are molecular substances, and they have intermolecular forces. Okay, and the melting points and boiling points are determined by the strength of the intermolecular forces. So we know now that hydrogen bonds are the strongest. So if I compare water to, say, hydrogen chloride will be dipole-dipole, water will be hydrogen bond forces, and we know hydrogen bond forces are stronger. Therefore, it will require more energy to overcome the forces. This is an extremely important phrase. If you tell me that you're breaking the forces, I'm going to mark you wrong. If you're telling me you're overcoming bonds, I'm going to mark you wrong. They're not bonds, they're forces between molecules. Here we have a molecule of water, and it is breaking away from the other molecules. Can you still see it's H2O? But now water is in gaseous phase. Okay, so the forces between the waters are being overcome by the energy we're giving it, and it's becoming a gas. Okay, so the stronger the intermolecular force, the more energy is needed to overcome, I've written it here, overcome the forces, and therefore the higher melting point or boiling point. Okay. Please remember, you've got to learn your different strengths of intermolecular forces, and you've got to learn if you've got two substances that both have the same intermolecular force, how do you distinguish them? Okay, read further back. So water boils at normally 100 degrees Celsius. This is at sea level. So everywhere in the world it will boil there at sea level. But because in Gauteng it boils at about 97, 98, because we have less pressure up here. Remember, if you're at sea level and then you're moving up, and this is the atmosphere, look how much atmosphere is pressing down at sea level, and look how much atmosphere is pressing down up here. And so we've got this force or pressure that's pushing down from the air around, that's now determining that these molecules now have to overcome that as well. And so you'll need more energy to overcome at sea level, because you've got much more pressure, you've got more air pushing down, and so it will require a little bit more energy to break through that pressure. Okay, right, last one, electrical conductivity. So metals and graphite, oh, the storm's coming, I'm going to talk quickly, can conduct electricity due to a delocalized electrons, okay, which are free to move. We know that metals have delocalized. There's all those little red dots are delocalized. But graphite, so like in your pencil, also has delocalized electrons, because not all the carbons electrons are bonded, so that's why they are delocalized, and that's why carbon or the graphite in your pencils can conduct electricity. Ionic compounds can conduct electricity, but only if they are molten. So if we can melt sodium chloride, it can conduct electricity, or if we dissolve it in a solution. Okay, this is because, remember, electricity is moving of charges, so, and ionic compounds are full of charges. And so if they can't move, if they're in solid, they can't move, so you can't conduct electricity. But if they're liquid, they can move, or if you dissolve it in water, they can move and it can conduct electricity. Okay, as ionic compounds are made of charged ions, they can conduct electricity, but only if the ions can move. So here we have a block of ionic compound. If we melt it, they can move. If we dissolve it in water, they can move. And so there it is. But look how much energy it took compared to that. Okay, so yeah, there we have it. Girls, please watch my videos over and over and over, and please, please, please ask me if you're not understanding. I'm going to be here for you right now for you to do these. I think I've given you tomorrow's hour to do this, so please, 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 you're doing it during that hour, so I'm there to help you. Okay, if I need to, I'll do a Google Meet with you if you are desperate for that. Okay, right, I love you, take care, and let me know.